This module introduces AC machines, and so here we will see sinusoidally distributed windings. I'm sorry, let me just change this here to a pen here. We'll look at ideally we should have a sinusoidally distributed winding, air gap field distribution due to such windings, and usually we have three phases. So what happens when we have three phases excited simultaneously, and how we can use space vectors to represent sinusoidal distribution. So that's the topic of or topics of this module. So we have primarily two types of machines. One is induction machine, another one is permanent magnet AC machine. So we'll look at both, but they have different rotor construction. But on the stator, you may say that they both have three-phase sinusoidally distributed windings as shown here, phases A, B, and C, and so they are represented by these three windings over here, and their magnetic axis is also shown as A, B, and C over here. And we'll assume the rotation to be counterclockwise here. So let's just look at one of the three phases, phase A, for example, as shown over here. And ideally, so this is ideally speaking, we would like a sinusoidally distributed winding for phase A. So you can see that the current is going into one conductor, 1, and is coming out of 1 prime, is going into 2, and then it comes back and comes out of 2 prime, and so on. But as shown here, the conductor density distribution is sinusoidal in the sense that there are very few conductors along theta equal to 0, which is the magnetic axis, and maximum number of conductors 90 degrees from this magnetic axis here. So this conductor density distribution can be represented between 0 and pi in this range over here by this expression here, some peak value times sine theta. So you can see when theta equals 0, you have very few or 0 conductors, and similarly at pi, but at 90 degrees we have the maximum. So if you integrate this from 0 to pi, we can see that we have total of n sub s number of conductors on each half here, and this is equal to 2 times the peak conductor density here, n sub s prime. Okay, so that's how these conductors are sinusoidally distributed within this winding over here. So given this, we can find what the, let's say we produce or send a current IA, what would be the field density distribution, our magnetic field intensity distribution here. So we can take a path here at some angle theta here. Let's say you have A sub A crossing this along this air gap here, and minus H sub A over here, but in magnitude they are the same. And so using Ampere's law and going through these equations, we can see that at any angle theta, the field intensity can be expressed by this expression here. So it depends upon the angle theta, and of course it depends upon the current at that instant. That is, so this is at any instant of time, let's say t1 over here. Okay. So given this here, field intensity, we can find the flux density and we can find the MMF distribution as a function of theta. So all these quantities have the same distribution, but they have different magnitudes and units, but the same shape. So what we are showing here is that at T1 and T2, let's say we have some positive value of I sub A, and the field distributions are shown here, whereas at T3 and T4, we may have negative current, and the field distributions are shown accordingly. But the point to note here is that the field distribution, whether it's flux density or whatever, is maximum along this magnetic axis here of this phase A. Similarly, it will be maximum along the magnetic axis of phase B and phase C here. So, that is what's shown here, that for three different values of currents flowing in these three windings, of course, all these three have to add up to 0, and so each one in the air gap is producing this flux density distribution, and the resultant of these three can be obtained point by point by adding them up at each value of theta, and that is given by this here. So this is pretty tedious stuff. You have to add point by point, but why not use vectors? So that's what we'll do. We'll use space vectors to represent sinusoidal distribution. So at any time t, whatever that time is, and whatever current we have in any given winding, that particular winding is producing a field distribution which is sinusoidally distributed. And you can see that if the current is in phase A is positive, the field distribution would be peaking along phase A magnetic axis. So we can represent that by a space vector. So a space vector has the orientation where the field distribution is peaking, and it has the amplitude based on how much is the peak of that field distribution. So here is an example where you have certain value of IA, which is positive, certain value of IB, which is negative, and certain value of IC, which is negative, but with the sum of all these three currents is equal to 0. And because of this IA, we have the MMF space vector for phase A in this direction. Because of B, which is negative, instead of being along the B axis, it's opposite to B axis over here. Similarly, for C, since the current is negative, it's over here. And so to find the resultant MMF distribution, rather than adding point by point, we can add these three space vectors vectorially as shown here, FA, FB, and FC over here. And so the resultant space vector is F sub S over here. So that very easily gives us the orientation where the resultant flux density distribution is peaking, and it also tells us how much that is. So mathematically, that is what's shown over here. So here is an example where IA is 10 amperes, IB is minus 10, and IC is 0. Some very simple example over here, and we are asked to find the resultant flux, MMF space vector here. So it's very straightforward. We plug in for IA here, IB for here, and IC is 0, and we find this, and that is what's shown over here. So we will take it from here and see how we can use it. So here is the summary of this module. It shows that we have ideally in an AC machine sinusoidally distributed winding for each phase, but that's not usually what we have, but we try to approximate that, and we can discuss that more. Then because of these sinusoidally distributed windings, we have air gap field distribution, which is sinusoidal, and in most AC machines we have three phases which are simultaneously excited, so we can make use of space vectors to represent these sinusoidal distributions.